Hang on. So it's going to be easier for you to transition from um, transfer these kinds of small files rather than these big files. So how can you get more accurate parts to be built using additive manufacturing? So that is the whole key behind making functional components using additive manufacturing. So the more triangles you have, the more size of the file you have. And if you have a flat triangle, if you have a very complex geometry shape, especially curved surfaces and microstructures and things like that, it really cannot exactly convey that information to the machine actually building this part. And if you have higher and higher printer resolution, it's not going to be very accurate. So you can see that these are extremely important, and this was based on a survey taken for many different groups of people, and they looked at what is important for them as far as the CAD software as well as the interfacing software is concerned. So they said that they wanted it to be non-proprietary, because you should note that most of the earlier files were based on proprietary software that was different for every single additive manufacturing manufacturer. So once you had one machine, you would always go back to that particular manufacturer to replace it. You are not going to go and look at another model or another material. And based on this, you can see that especially the geometric fidelity is one of the top requirements of additive manufacturing users. It's extremely important. Now, I'm sorry, there is a small mistake here. It should be planar patch. But what you can see is that this kind of a triangle, you can't use that to fill all the space. If you really want to accurately fill all the space without creating any gaps, you need to have curved using vertex normals or curved patches. I mean, even this is not sufficient. And where it will come into play is when you have extremely complex geometry. I will not go too much into the depth of all this. I mean, this is the kind of things that go into the actual component building. So when you look at a simple case, so suppose your software can build these kinds of rectangles and use that to fill space. This is not very accurate. So your final component is going to have a lot of surface finish issues, and you will have areas where the material has not been filled properly and things like that. So in order to increase the accuracy, what do? You have to reduce the number of, you have to increase the number of rectangles, triangles. If you want more accuracy, you go to even further subdivision of the triangles. But more the number of triangles, higher the size of your file. So suppose you had a simple shape like a ball made of this. So you can create these rectangles, or in some places where you might be able to put some kind of a quadrilateral or rhombohedral type of faces. You can see that, but it is not very accurate. So it's going to have some kind of a facet type of a build. If you want even more accurate parts, you have to increase the number of rectangles. So it will increase the time to build it, but That's the only way to increase the accuracy of your parts. So, for example, um, if you had a part that were 20 triangles, they call it icosahedron. It's going to have a certain level of accuracy because you are going to have facets there. So if you really want to represent that, and you are trying to create and you had actually been trying to create a ball, um, a nice uh, with a nice surface finish, nice rounded edges and things like that. And if your software can only build flat triangles, that means there is a 10.26% diameter. So your final part that is to be built is going to have errors with respect to your actual model that you want to build. If you had icosahedrons with triangles, you can reduce that error to 3.81%. But if you want it even less error, you can reduce each of these divisions by twofold. It reduces that down to 1.49%. Threefold means the error goes down to 0.84%, and it can go down to 0.67%. Now, there is a limit to the maximum reduction in error. So see the previous one, 0.67, and this is 0.635. So just imagine the time it takes to build this part, and still you're only able to reduce it down to 0.635% error. Now it is down to 0.625, but you have increased your build time by maybe 2 times. So there is a maximum reduction in the number of uh, triangles that you can, number of subdivisions that you can do, but it can only go down to maybe maximum 0.6% error. Suppose you had even more. I mean, like, if you are going to be representing this circle as double icosahedron, and you keep on increasing that, here you might be able to get it down to 0.068%. So that might be a better way to get accurate parts compared to the other one. So what it shows is that by multiplying the number of triangles that you are using to represent a surface, you can reduce the error percentage compared to the actual part that you have designed. Okay, so it can be brought down using surface normals of the triangle patches. Okay, so these are the different error reduction methodologies in your design approaches. So depending upon the design approach, you can reduce your error, but that increases the time it takes to build the part. Okay, so this one is curved triangle, so that's the maximum you can do with STL, and this is with AMF curved sixfold. So let me uh, again, I mean, you can see that from STL to this one, um, you can see that it can reduce it by considerable amount. if you reduce the number of triangles. Okay, so again, this talks about accuracy, different accuracy percentages and things like that. And these are some examples. So let me stop here and get to the next set of slides.